Welcome back, everyone. Today our lesson is on concavity and points of inflection. Okay, so first we're going to talk about concavity and what the different types of concavity we can have in a graph. So the first one is concave up, and concave up would look like that. And we say that it's shaped like a cup. So it smiles, it holds water, lots of different ways that you can remember that it is concave up. Now, if you look down here, it says the first derivative is increasing. Please make sure we're getting this in our notes, okay? This is important. The first derivative is increasing, so the second derivative is positive. All right, so what's that all about? How is the first derivative always increasing? Well, if I look at the slopes here, remember the first derivative is talking about the slopes. Okay, so if I look at the slopes as I go through this graph, so if I want to draw in like little tangent lines, I can see that right here it's very steep negative, maybe like a -8. And then here it gets a little bit less, so maybe like a -3. And then here maybe like a -1/2. And of course then I have my 0. And then coming up I have like maybe a +1 and then maybe like a +5. So you can see as you're looking at those slopes, as you're moving from left to right, what's happening is those slopes are getting more and more positive. They are getting larger and larger. And so we can definitely say that the first derivative is increasing. So the second derivative is positive. So what I want you to remember is increasing and positive. The way I can remember that is think of it as making a very happy smiley face. Okay, so that's concave up, shaped like a cup. The next one is concave down, shaped like a frown. Okay, so concave down, shaped like a frown. So there's your frowny face. It is spilling water out. And now this one says that our first derivative is decreasing and the second derivative is negative. Again, get those in your notes. This is important. So how is the first derivative decreasing? Well, again, let's look at those tangent lines, okay? Here, if we start on the left-hand side, now we're going to have an extremely positive, so maybe like a +7. And then they start to get a little bit, so maybe that's like a +1, and then 0. And then we get into our negative slopes, so like -1, and then like -6. Okay, and so what happens here is that now as I look at these slopes and compare them from left to right, what's happening is they are definitely getting smaller and smaller. So the first derivative is in fact decreasing, making the second derivative negative. And so now, to finish off our face here, we would go ahead and put a very frowny face. Okay, so that should just kind of help you remember decreasing and negative on the concave down, shaped like a frown. Okay, the last type of graph that we want to talk about in their concavity is just a linear graph. So if we have a linear graph, we know that it is just a line. Okay, and so if you look here, it says the first derivative is constant. Now I didn't have to draw it that way. I could have drawn a line like this. I could have drawn a line like this. For either of these, though, the first derivative, the slope, is constant. If you think about it, the slope is a set number. So say the slope here is +1, or the slope here is -4/3, or the slope here is 0. Okay, no matter what the slope is, it's constant. It does not change. And so, therefore, if the first derivative is constant, then the second derivative is 0. Okay, the next big concept for today are points of inflection, oftentimes called POI, for points of inflection, obviously, or inflection points are another thing that, another way that we sometimes talk about them. So if you're looking at a graph, okay, you can see in this graph that there are times when the graph is concave down, shaped like a frown, other times when it's concave up, shaped like a cup, concave down, and then concave up. And so what we're talking about here, the points of inflection are the points for which the graph switches from concave down to concave up. So if I look through my graph, I would be able to say that right here, for example, would be my first place where I would say there is a point of inflection. Because to the left of it, I am definitely concave down, and then to the right of it, I am concave up. Okay, the next point of inflection, hopefully you can look at the graph and see, would be right about here. And that's my next POI. Because again, now this time I'm switching from concave up to concave down. And then the last one and again, hopefully you can recognize this, is right here, and that would be your last point of inflection on this graph. Because again, you are switching from concave down to concave up. Okay, so we're going to go through several examples here, but before we do, there's some important information that we need to know. My daughter's going to read the first one.
Possible points of inflection. The values that will make the second derivative 0 or undefined are the possible points of inflection.
Thank you, Abby. Okay, so just like we talked about finding the first derivative and finding the critical values for the first derivative, when we are talking about increasing intervals of increase, intervals of decrease, and relative mins and maxes, or absolute mins and absolute maxes. Here, when we're talking about finding our intervals of concavity, or when we're talking about our inflection points, we again need to find critical values, but this time it's for the second derivative, and the same concept exists. It's when your second derivative is 0 or undefined. Okay, those are your critical values, and then we're going to make a sign chart just like we did with the first derivative for relative mins and maxes, and we are going to be looking for intervals for which the second derivative is greater than 0 or positive. Then it means that it's concave up. Okay, so if we have greater than 0 for the second derivative, then we have concave up. If we have less than 0 or negative for the second derivative, then we know our original function is concave down. So the second derivative communicates to us about the concavity. Okay, so our first example. State the intervals on which the graph of the function is concave up and concave down, and the coordinates of any points of inflection. Now I want you to recognize that they're asking for the full coordinates, so that's going to become important at the end. All right, so we're given this function. Now, as soon as we're talking about concave up, concave down, points of inflection, that tells us we need the second derivative. Okay, so we need to memorize that if they're talking about concave up, concave down, or points of inflection, we're getting the second derivative. So I'm going to go through and first find my first derivative. All right, that would be 12x minus 4x cubed. And then I'm going to go ahead and take the second derivative. So I'm just jumping right from one to the other. It's 12 minus 12x squared. Okay, so now I'm going to go ahead and set that equal to 0 so I can find my critical values. Okay, so I'm going to go ahead and factor out a 12 here, 1 minus x squared, and then obviously that factors into 1 plus x and 1 minus x. So when I tee it up, I get x equals negative 1 and x equals 1. All right, so those are my critical values. All right, and so I am ready now to make a sign chart with those critical values. So when I do that, okay, I put those on there, negative 1 and 1. Those are my zeros. Now, we have to recognize that we're talking this time about the second derivative, but our second derivative now is communicating to us about our original function f. Okay, so now what we need to do is go ahead and test values to the left of our critical values, so like negative 2, in between, so like 0, and to the right, like 2, into our second derivative. So we're plugging it into our second derivative, which is right here, okay, in fully factored form. So if I plug in negative 2, I get 1 minus 2, which would be negative, and 1 minus negative 2 would be positive, so negative times a positive is a negative. That tells me if the second derivative is negative, then I know that I'm going to have concave down here. Okay, now I'm going to go ahead and plug in the 0. So 1 plus 0 is positive, 1 minus 0 is positive, positive times a positive is a positive. If my second derivative is positive, then I know I'm going to be concave up in this interval. All right, now I'm going to go ahead and plug in the 2. So 1 plus 2 is positive. 1 minus 2, though, is negative. So a positive times a negative is a negative. And now I'm going to have another interval of concave down. Okay. Okay, so I can start to make my conclusions about my intervals of concavity. I can say that I am concave up in the interval from negative 1 to 1. And my justification or my reason would be because the second derivative is greater than 0. I can say that I am concave down over the intervals negative infinity to negative 1 and from 1 to infinity. And that would be because my second derivative is less than 0. Okay, the next thing that they're asking are for the coordinates of any points of inflection. So if I look at my sign chart here, I can tell that I am switching from concave down to concave up. So right here would be your first point of inflection at x equals negative 1. And then I go from concave up to concave down, okay? And so right here would be my second coordinate of a point of inflection. So now what I need to do is get my y value for those points of inflection. Okay, so these are my x values, the negative 1 and the 1. What I need is my y values. And now this time, because I'm searching for the y values on the original graph, on the original f graph, I have to plug those in back into the original. Okay, so I'm going to say f of negative 1 is equal to 6 times negative 1 squared minus negative 1 to the 4th. So that would be 6 minus 1, which would be 5. Okay, and then my second point would be f of 1. And plugging that in, I have 6 times 1 squared minus 1 to the 4th. Same thing, it's going to be 6 minus 1, so 5. So I would say my points of inflection, okay, so points of inflection would be at negative 1, 5 and at 1, 5. And the reason why, you can just make a general statement that points of inflection because f double prime changed sign. Okay, the second question tells us to consider a differentiable function f with the given first derivative. So make sure that you catch that. They're giving us the first derivative. Find the x coordinates of any points, of any inflection points, and then state the intervals in which it's concave up and concave down. So this time they're a little bit nicer. They're asking just for the x coordinates of the inflection point. So we don't have to find the x comma y. We just need the x values. All right, so if they're giving us the first derivative, in order to go ahead and find the intervals of concavity, we need the second derivative. So I need to go ahead and take the second derivative of this given function. And looking at our function, we can tell that the first derivative is a product, so we're going to use our product rule. So first would be x squared times the derivative of the second. Well, okay, so I'm going to have to use the chain rule. So 3 times, keep the inside, x squared minus 4, drop the 3 down to a 2, times the derivative of the inside is 2x. All right, so that was first times the derivative of the second plus the second, x squared minus 4 all to the third, times the derivative of the first, which is 2x. All right, so if I kind of clean this up here, I have x squared times 3 times 2x would be 6x cubed, and then x squared minus 4 to the second, plus my 2x, x squared minus 4 to the third. Okay, so if I can take out a GCF, I should, and I definitely can take out a 2x and also x squared minus 4 to the second. So again, I was looking at this term and what's in common. All right, and then what's left over when I divide that out from both of them, on the left-hand side here, I would be left with 3x squared. And then on the right-hand side, I would just be left with an x squared minus 4. Okay, so cleaning that up one last step. In here, 3x squared plus x squared would be 4x squared minus 4. Okay, so there is my second derivative. All right, which now, if I want to find the intervals for which it's concave up and down, I need to find its critical values. So I'm going to go ahead and set this equal to 0. And if you look, it's already in factored form, okay? 2x is one of my factors. X squared minus 4 squared is a factor, and 4x squared minus 4 is a factor. So I'm going to set each of those factors equal to 0. So in this first one, I get x equals 0. This next one, If it's a multiple, x squared minus 4 squared, I just have to deal with the inside. So I get x squared equals 4. So x is going to equal positive and negative 2. All right, and for this last one, I would have 4x squared equals 4. So x squared would equal 1. So x would equal positive and negative 1. Okay, so we end up with 1, 2, 3, 4, 5 critical values that we have to put on a sign chart. Okay, so I'm going to go ahead and set up my sign chart. And remember, of course, this is f double prime on the top, and it's telling us about f, the graph of f. And so I have negative 2, negative 1, 0, 1, and 2. And those are all my zeros. Okay, so now I'm going to go ahead and plug in values to the left, in between, to the right, all that kind of stuff. Okay, so if I plug in a negative 3, I would get a negative times a negative 3 squared would be 9 minus 4 would be positive. And then times, let's see here, that would be 9 times 4 is 36 minus 4 is also positive. So negative times positive would definitely be negative. So that's going to be concave down. All right, plugging in a number in between negative 1 and negative 2. So it stinks, you got to plug in a fraction. So like negative 1.5 would be negative times, all right, negative 1.5 squared would be like 2.25. Minus 4 is definitely negative, but then you're squaring it, so it's going to be positive. So this middle one, this middle factor here is going to be positive no matter what because of the squared. Okay, and then we said that negative 1.5 squared is 2.25 times 4 is definitely larger than 4, so that's going to be another positive. And so we end up with negative again, so concave down again. All right, between 0 and negative 1 would be like negative 0.5, so again it's negative. We said the middle term is always going to be positive. And let's see here, negative 0.5 squared is 1/4 times 4 is 1, minus 4 is negative this time. So negative times negative is now a positive, so we're going to have concave up between those two critical values. All right, plugging in 0.5. So now you're going to see a lot of repetition here. The only difference is that your first term is always going to be positive now, because if we're multiplying 2 times positive, it's going to be positive. And then the middle is always positive. And then we already said that last one is negative, so we're going to have a negative here. So concave down again. Okay, between 1 and 2 would be like 1.5. So that would be positive and a positive and a positive. So we're going to end up with positive. So concave up. And then like if I put a 3, I have positive and again positive. So I end up with concave up. All right, so if you look here, if we want to describe our intervals of concavity, we can tell that we have definitely some repeating. So we're down, and then we are down, and then we're up, down, up, up. All right, so if I talk about all of the intervals where I am concave up, that would be starting here at negative 1 to 0, from 1 to 2, and from 2 to infinity. And the reason would be because the second derivative is greater than 0. It's positive. Okay, I am concave down from negative infinity to negative 2, from negative 2 to negative 1, and from 0 to 1. And that would be because the second derivative is less than 0. Okay, now the other question it asked for was the x values of the points of inflection. So anytime I'm switching signs, either from negative to positive, like as in here, okay, or from positive to negative, these x values are points of inflection. So I would say that my points of inflection occur when x equals, let's see here, negative 1 and 0 and 1. And that's it. So at -1, 0, and 1, and that's because, the reason would be because the second derivative changed signs. All right, consider a differentiable function with the given second derivative. So this time they were nice, they gave us the second derivative. Find the x-coordinates of any inflection points and state the intervals in which it's concave up and concave down. So again, we need to be looking at the second derivative, which they nicely give us. All right, so I'm going to ask you to go ahead and pause, find your critical values, set up a sign chart, and answer the questions. Tell me the times when it's concave up, concave down, and tell me the x values, the x-coordinates of the inflection points. Okay, so go ahead and quickly compare your work. You should have gotten critical values up here of 0, 3/2, and positive and -3. So I put those on my number line here, my sign chart here. Okay, I labeled the top as F double prime and the bottom as F. And then I tested values. Some shortcuts. A negative number cubed here is always going to be negative times a negative. So that's why the first one's always going to be positive anytime you test a value to the left of 0. Okay, my middle term here is to the 4th. Any number to the 4th power is going to be positive. So if you look, all of my middle values are positive. And then it's just really testing it into this last one. And so you can see the signs that I got and their concavity then for the graph of F. And there's my conclusions. My points of inflection occurred whenever I changed sign. So that occurred here when I changed from positive to negative, here when I changed from negative to positive, and then at +3 when I changed from positive to negative.